year and running a packed event across 5 days. It's a hybrid event. We're running an in-person day on Wednesday, and you can look up our schedule and join us for that day. And today we're we're welcoming Ventatesh Kannan, who's going to be telling us about the next stage in the journey of quantum computing and where it's going. So the festival is running over 5 days. You can follow us on AtlanTec Fest and use the hashtag AtlanTec. There's a Q&A function for the session itself. I'll follow that. My name is Ian Gallivan. I'm working with the NUI Galway Innovation Office. I'll be taking your questions. I'll be fielding those and sending them to Ventatesh. So in the meantime, let's hand over to Ventatesh and let's take the session on from here. Okay, thank you. Bye-bye.
Thank you very much, Ian. Hello, everyone. I'll just take a minute to share my screen. Okay. So thanks very much, Ian, for the introduction to the session. As Ian mentioned, last year, I believe, we had a similar session on introducing quantum computing as an emerging computing paradigm to the audiences. So in today's session, what we'll try to do is probably bridge the gap between what we kind of covered last year in introducing and positioning quantum computing, and perhaps cast an eye on where the technology and its use currently has progressed, and what more importantly lies ahead in terms of the quantum computing systems coming into their being. So the rough agenda, it's probably not strictly X slides for each of those topics, but what we would probably like to touch upon is why has quantum computing been of particular interest to a large audience, not just technology developers, but the end users in a number of domains. Why is quantum computing being so widely discussed in a number of channels? And where is currently the action happening in quantum computing, and what are the opportunities for us as different stakeholders in the quantum computing landscape? What are the opportunities for us to engage, to monitor, and to contribute potentially? And to be able to do that, what is kind of the value chain? So the value chain is probably pretty identical to many other technologies, but also who are some of the key stakeholders, and particularly their roles in the development of the quantum computing technology and its applications. And also then we'll probably touch towards the end on what are some of the national level opportunities to engage with quantum computing as well, if you're indeed interested in dipping your toes or diving headfirst into the domain. So just as a quick summary, this is probably used in a number of places. Just to recap for those who are probably relatively newer to this, the computing technology has evolved over the decades quite a bit, from different form factors of devices, from transistors to microprocessors. And the quantum computing is actually the next paradigm shift in how the subatomic and atomic level particles are being used for both representing data as well as for processing them. So things are getting smaller and smaller in terms of digital devices, and that particularly is the reason why the next paradigm shift is towards quantum computing. So what this means is, in the classical computing paradigm, we have been dealing with the binary logic where we have ones and zeros represent data. So all of this is probably better understood by most of us as to ones and zeros are stringed together to represent different data and also different computations. What happens though in quantum computing, it's you no longer deal with either or, but a probability associated with potentially all possible states in which data can exist for a certain attribute. So what this means is this allows for potentially massive representation of data at scale with a limited set of storage entities, which are called qubits, and then to be able to process them in a lot more parallelized way. Due to the inherent property of quantum mechanics, we are able to explore or process, so to say, those large states of data in almost parallel. So that's where the advantage of quantum computing comes in at a very high level, which is extreme scale or space of data being represented in a lot more concise fashion as against what a classical storage device would allow, and being able to do extract a lot more parallelism from that. And typically where this comes in handy is what is illustrated at the bottom here. There are a category of problems which are relatively easier to solve within a finite amount of time on classical devices. But once the tractability of those problems becomes harder and harder, the time to solution of the classical problems on classical devices is potentially exponentially increasing, for example. So the time to solution dramatically increases. And what we do currently to avoid a really long-running problem to solution or a time to solution problem is by either simplifying the problem through approximation or heuristics, or we basically preemptively terminate the problem. And so the accuracy of the result is kind of understood to be quite limited. So either at the expense of accuracy or at the expense of precision, we approximate the classically large or hard problems on the classical devices. And this is typical in case of, say, computational chemistry, or in case of physics, or optimization and search, and so on. And these kind of broader areas of physics, chemistry, and optimization, they have applications in a wide number of domains and sectors, typically in material design and on battery technology, or digital devices, or devising new molecular structures, either for drugs or for other materials, or in case of optimization or search. It has a wide range of applications. It can be in exploring the risks in a portfolio of assets, or in terms of logistics and probability safety assessment systems, and so on. So optimization wherever is a critical component or a step in an application domain. These kind of hard problems typically suffer from approximations or reduced precision. So it is in these hard problem areas where quantum computing is perceived to be able to deliver a huge leap in advantage going forward. Now, all of this meaning that the development of the technology, but also looking at what can quantum computing do for these problems, that is still being explored as the algorithms and the software capabilities progress to be able to program quantum computers as well. So as I mentioned very briefly, the most typical application areas in which quantum computing is being applied and explored as the technology develops are in material sciences, where this example is basically is the molecular structure, where the atom, the electronic structure is a conductor at a certain temperature, but then becomes is a conductor at a certain temperature, but becomes an insulator in a different temperature. So to be able to calculate the molecular, the electronic characteristics of this element is key to be able to design custom materials for specific purpose. And similarly in chemistry, even though there are limitations, so to say, in being able to fit large chemistry, large molecular structures in quantum computers. So as I said, the technology is evolving, but then the size of the molecules that can be simulated or the current classical devices is reasonable, but then at the expense of approximations and precisions. So going forward with the current types of quantum computing devices, we would not be able to fit an entire molecule, large molecule, so to say, like a protein for folding and designing a drug. That would not be directly simulatable on a quantum computing device yet. But what is possible now, or where the focus is on currently, is to break down these larger molecular structures potentially into smaller molecular fragments, and then do the simulation and the calculation of the likes of energy or other characteristics of those molecular structures, the fragments of those molecules on the current size of quantum chemistry devices, the quantum computing devices, and then aggregate the results from those fragments from a quantum computer onto the larger molecular structure. So people are coming up with, so to say, ingenious ways to cater to what a quantum computer can handle now by breaking down or dividing larger problems into smaller sub-problems and then fitting those sub-problems of smaller size on quantum computers so that they are exploring the potential advantage a quantum computer will be able to deliver in terms of more precision or accurate results. And similarly, in case of optimization, I had mentioned, and quantum machine learning is also well publicized in some areas. Now, this is a very interesting area of exploration. It comes with an exclamation mark, because where exactly quantum computing can aid the machine learning pipeline from analyzing a training data set, so to say, and then creating a machine learning model, and then applying the model on live data to do inference. In that pipeline, we would typically use larger data sets when it comes to paradigms like deep learning in machine learning to train a deep learning model. So we usually deal with megabytes or terabytes or even petabytes of data to train the machine learning models. But in quantum computing, we have to understand that the quantum computing devices are ones where they have very narrow input pipes and they have very narrow output pipes. And currently, quantum computing devices are also quite noisy. So in terms of the duration for which they can do a calculation is quite limited compared to the classical devices. So the size of the problems, but also the data that can be put inside a quantum computer through the input and output, that is quite restricted. So what we cannot currently do is to push, so to say, a large training data set for a neural network into a quantum computer and then do the whole neural network training in quantum computing. But what is being explored is, for example, in case of language models in machine learning, there are parts of a model which heavily would benefit from better optimization and search layers. So to kind of find the optimal parameters for those for those segments of machine learning models, quantum computers are being trained or quantum algorithms are being defined to find the better optimal parameters in the machine learning or the neural network training pipeline, so that we can get better accurate models out of it. So the hybrid nature of classical machine learning models with some elements assisted by quantum computing is where quantum machine learning is heading. But it's a very early stage for quantum machine learning, and there is a lot of exploration going on in that area as well. Now, in terms of applications, there is a lot of activity happening. But in terms of access to quantum computing systems, there is equally a lot of work being done to, so to say, to democratize quantum computing. This is primarily important because it's a very early stage, and much of the quantum computing technology and device engineering is informed by the kind of use cases and applications as well. So there is a huge emphasis based by many developers of the technology on a co-design approach, where it's just not an infrastructure or technology being created for some kind of use case, but the use case itself sometimes informs the device vendors and the device creators on how to define the parameters and characteristics of a device, because some devices potentially could be better suited for certain use cases rather than other device characteristics. So access to quantum computing devices vis-a-vis democratization of quantum computing resources is one of the key elements which we believe as someone that bridges quantum computing technology creation with its end use as a center that kind of bridges the gap. We see that that's going to be very important. And there are different mechanisms by which users currently can have access to quantum computing systems. Typically, what we get off the news is access to these, so to say, standalone quantum computing systems, which are represented on the top, where these are either accessible by a public cloud access mechanism that is provided either directly by the vendor or a public cloud provider. or at a remote organization or an institution where there is public access that is available to log into a certain quantum computing system and either undergo training exercises, learning exercises, or develop proof of concept solutions. So this kind of a standalone quantum computing system access is what we typically see in the public media. But behind the scenes, there are a lot more access mechanisms for getting one's hand on a quantum computing environment. So the software emulated quantum computing system is typically used by many in the community, where it serves as the stepping stone for gaining experience and exploring some of the early algorithms on smaller scale quantum computing devices. So the software emulated quantum computing systems typically tend to run on classical HPC systems, either on your desktop or laptop, or in public cloud, or in a HPC system that is provided by a national center, for example. So the software emulation basically characterizes or simulates the behavior of a quantum computing hardware, whether it is the computational characteristics or the noise model or the error, etc., etc. Those kind of characteristics of quantum computing devices are simulated in software, and they are pretty good in relatively accurately giving a quantum computing device experience. So this typically comes in hand where at the early stage of learning how to program quantum computers or exploring the implementation of certain quantum computing algorithms, these software emulated devices are very handy because they can be easily installed. Many of them can be easily installed on one's own laptops or just publicly available for free with support from the providers. Now, the bottom two are relatively emerging areas where quantum computing systems are being integrated in different modes with the classical high-performance computing systems. Now, these HPC systems are either available at national centers across many countries by the service providers, or they're deployed on the public cloud. So the integration of the classical HPC and quantum computing systems would have to happen through the entire stack, and it's very early days for that. And why it has to be done at full stack level, from hardware to software to applications, is because currently we are using GPUs as if they were pretty much hidden from a programmer's perspective. But 5-10 years ago, the programming of for GPUs, for general purpose computing, was a very specialized skill. But over the years, what has happened is that GPUs have been seamlessly integrated in hardware, in system software, and programming tools, so that they currently are almost hidden to the end user application layer. And similarly, something like that, equivalent of that, is currently emerging in the quantum computing paradigm as well, whereby potentially down the line, the quantum computing stack would have been seamlessly integrated, and it would almost relatively be invisible to the end user programming community. But this is an area where there is a lot of opportunity for technology development at this stage as well. And the way in which the integration is done is also quite diverse. You might have a quantum computing system that is physically closely located with a classical HPC system, or you might have a network of quantum computing and classical computing infrastructure that is geographically diverse, but then their interfacing mechanism through software would allow for execution of hybrid workflows and remotely executing quantum computing and classical computing jobs. So these are different paradigms that are being developed as we speak. But then the access to quantum computing systems themselves, as I mentioned, maybe a bit more detail. A good first step in our experience in engaging with end users in academia and industry for the early stages is to use the software simulator or software emulated environments, and there are a number of them that are provided. Some of them come from the technology developers of quantum computing, like IBM or Microsoft or Google. Like the software simulator from Google is a part of their programming framework called CIRC, and similarly, the software simulator from IBM is a part of their Qiskit framework. But then there are other developers like QLAX or the Atos quantum learning machine, who provide standalone software simulators of quantum computing systems. So these are typically a very good stepping stone for getting one's experience started. And these are equally important because when we come to using physical quantum mechanical devices, there are a lot of noisy error related characteristics that are associated with these kind of hardware devices, where the learning curve of running an algorithm on a physical device could be quite huge. So there is always a two-step or a two-phased approach that we see emerging, where the learning is done on a quantum software simulator, and then that works as a stepping stone for then running the algorithm or porting it to a quantum mechanical device in the background with support from the device developer. And finally, the quantum computing systems in the middle are pretty much developed and offered by commercial or enterprise developers, both within Europe but also internationally. And on the right side, there are community-driven efforts. By community, I mean through HPC centers or through funded projects from national or European programs, whereby systems are developed for national users access or for European access. So the Quantum Inspire, for example, is developed by the Dutch HPC Center and the ecosystem there, whereas the HPC QS under the Euro HPC joint undertaking is a program that is pan-European, where 12 different organizations from across 6 different countries in Europe have come together, including iCheck in Ireland, have come together to integrate the quantum mechanical devices with the HPC devices and provide access to them to national and European audiences. And similarly, the quantum learning platform is something that is being established at a national level for access. And the one in the bottom right corner is the Nordic Quest initiative, where Finland, Norway, Sweden, Denmark, and a few other Nordic countries have to come together to kind of create a network of quantum computing and HPC resources for access to European audiences. So there are a wide range of access mechanisms, but a good first best practice approach seems to be to learn with the software simulators and then go on to the hardware devices themselves. And briefly, before we perhaps go on to how to kickstart one's engagement with quantum computing, I just wanted to briefly present what kind of value chain and key stakeholders are currently actively involved in the development of the technology. So just working anti-clockwise, from the left corner in the orange or red are basically the fundamental theorists, the physicists and the engineers who are actually working with the quantum mechanics and the device engineering level at the hardware level to build these quantum mechanical devices, the quantum processing units. And then in the green are the people or the category of key stakeholders who bring these devices, the QPUs and the quantum computing systems, into an environment where the users can have access to these devices either through national services or through commercial services. And the system software developers and algorithm developers are key in basically establishing, one, the software that is required to program these quantum computers, whether they are low-level system software or programming tools or programming libraries, application libraries, or the algorithm developers basically define the domain-specific algorithm or the problem-specific algorithm, which is at the end of the day then being used by the end users. Then the ones on the blue on the right side are basically the application developers that leverage the technologies that are developed by those in the green and the red. So the application developers typically tend to leverage the algorithms and the programming toolkits to program on these quantum computing devices. And then the technical managers, the executives typically in enterprises, find a viable technology case or a business case for pursuing or adopting quantum computing into their technology portfolio. But typically the most important we see kind of stakeholders currently that are coming up are the trainers on the top, the skills developer people. So the trainers typically would deliver the capabilities of teaching people on how to develop algorithms and applications on quantum computing devices. And typically these trainers we see are required to have a blend of skills ranging from the domain expertise, whether be it in chemistry or in machine learning analytics, data analytics, or in optimization problem mathematics. So the domain expertise is one. Secondly, also experience in quantum mechanical devices and algorithms and the mathematics involved in the programming categories, and the programming tool chain. So just to summarize that part, the skills for quantum computing applications is a huge area where a number of training programs by different organizations are being developed. So vendors like IBM or Microsoft or Intel develop their portfolio of learning material and learning environments, whereas there are other national programs and institutional programs where quantum computing is taught from the mathematical perspective, the physics perspective, that the applications perspective, and the algorithmics perspective. But then at the end of the day, what we are seeing as a convergence in the community is that for developing or for programming quantum computers, the three key ingredients of skills that are required, and typically these come from different communities within a certain project, is that the domain expertise for the likes of natural language processing, or for molecular chemistry, or for data analytics, or for financial services, the domain expertise always resides in the end user or the stakeholder. Then there are a category of people who understand the quantum mechanics and the information processing and the mathematics behind quantum programming, who are developing then the quantum algorithms and applying them for specific application areas and the use cases. And typically the domain experts and the quantum algorithmists and programmers work very closely together and need to establish a language of communication with each other to understand each other's area of expertise. And then the quantum computing systems expert, basically, typically when we want to run or port the applications that are being developed on quantum computing devices, then those vendors who are closer to developing the technology actually bring the expertise in how a piece of algorithm or an application that's developed can be run most efficiently in the specific device, because that is a non-trivial problem in running a quantum algorithm or a use case on a certain quantum software simulated environment, or one device onto another device. So it takes a lot of device expertise to run an algorithm or an application on a specific quantum mechanical device. So this is very typical in many of the projects that iCheck does. And one key example is with Accenture. We've been building over the last few years a quantum chemistry simulation pipeline whereby molecular structures can be simulated on quantum computing devices. And the team typically comprises of a computational chemistry experts with quantum algorithm experts. And then more recently, since we have moved from a software simulated environment to a hardware environment, we typically are having to engage with the hardware developers to better understand how the characteristics of the hardware influence the results or the computations for the quantum chemistry use case. And finally, to address the skills development area, what iCheck have been pursuing for a good 2 years now is a quantum programming certification course, where we have engaged with different enterprise organizations and public sector organizations in Ireland to find out what are the key pain points, so to say, what are the key areas of interest where skills development is perceived in quantum computing within Ireland. And typically what we have come out with is a recommendation where the executives in an enterprise organization, the technical managers and the developers would pursue different pathways, learning pathways in getting skilled up in quantum computing. So the quantum programming certification course that is currently under preparation and is soon to be delivered basically offers a customizable learning pathway for these three different categories of employees within enterprises, particularly with the focus on executives to be able to identify the impact that quantum computing can bring to their organization, their solutions, and to be able to then devise strategies for their business development or their investments in learning quantum computing within their organization. The technical managers, or basically the senior leadership, the technical leadership, typically work on watching the technology evolution of quantum computing, and then at the same time to be able to identify key tipping points or the capabilities that the organization would need to develop within quantum computing, either on a project basis or through a learning basis. And finally, the people that do the hard work, which is the developers or the engineers or the scientists, would in the quantum programming certification course would do a lot of hands-on in terms of understanding the algorithms and the tools, the software programming tools, to basically build demonstrator or proof of concept use case applications, which would lead to then a more skilled task force within an organization. So without going into too much of the details of the certification course, the content of the course itself, as I mentioned, offers a customizable learning pathway for different types of enterprise employees. But then the portfolio of modules or content that is composed within the quantum programming certification course is broadly organized as 5 different themes. The first theme would introduce the potentials and capabilities and limitations of quantum computing, and then it would be followed basically by a theme that would focus on how quantum computing systems are engineered and are available for access, and how quantum computing devices work to a certain extent in reality. And then the third theme focuses on basically laying down the fundamentals in terms of the physics and mathematical knowledge to be able to work with quantum computing algorithms and the programming requirements. Then the fourth theme basically builds on the previous 3 experiences to provide, so to say, a landscape of quantum computing algorithms that are currently available, and also how they can be mapped onto different applications within different domains. And then finally, the theme 5 is focused on identifying what are the currently available software development toolkits and programming libraries in quantum computing, and how one or more of them are of interest to an organization and can be used to implement these algorithms in practice. Now, the executives and the program managers can basically stitch the modules together to their requirement. But typically, what we have seen is desired among the audience is that the executives understand what quantum computing can and cannot do, and how quantum computing functions within the ecosystem of classical computing technologies that they already might be using for some of their products and solutions. The one for managers on the right side basically goes a bit deeper into understanding how quantum computing devices are practically realized and can be accessed, and also an introduction to what are the types of quantum computing algorithms and programming tools that are available for different application areas. And finally, the longest or the most detailed version for developers goes beyond that in delivering the mathematics and the details of the quantum computing algorithms, and the attendees basically have an opportunity to define a tailored project and pick maybe one or more software programming toolkits or libraries to explore a certain set of quantum computing algorithms for their targeted domain of expertise. So just to summarize, quantum computing, since we spoke last year, a lot is happening, but it's rapidly evolving, and there are parallels with how cloud computing and map and visualization and AI have kind of been hugely impactful on our consumption of computing technology. So there are parallels with how much of an impact quantum computing is potentially likely to have on high performance computing. Now, the technology development as well as an understanding of how it has to be used in terms of applications is still emergent. So quantum computing is not yet ready, but the technology is rapidly evolving, and there is a lot to develop going forward. But equally importantly, there is a lot more to do currently in terms of skills development, especially in identifying what kind of algorithms, application areas, and use cases are going to be most relevant for different industries, different application sectors currently, because early adoption of the technology is absolutely being prioritized by many organizations. And to be able to do this, one of the good practices that we have identified through our engagement is for organizations, enterprises or public sector, or even in research and development, to identify their position, the organization's position in the quantum computing value chain, whether you would want to co-develop some of the technology, whether it's hardware or software or algorithms with the ecosystem, or you are more of an end user where you leverage existing software programming toolkits and algorithms and pretty much acquire skills and develop solutions with them. So identifying and positioning within the value chain is definitely one of the starting steps. The second is naturally then to identify or define what are the short-term and medium-term learning objectives, whether you would like to acquire some higher level skills in terms of identifying the technology roadmap and what are the key areas of the quantum computing development pipeline, or whether you would want to invest time in skills development within people. So identifying both short-term and medium-term learning objectives are critical currently. And the third one is it's a hugely open community, quantum computing, because a lot of breakthrough innovation and results are being published through collaboration between the technology developers as well as the end users. So there's a lot of vibrant community where people are equally engaged in working with each other. So identifying and engaging with collaborators is definitely one of the strengths of the quantum computing community now going forward. And then naturally, the last 3 points are basically where the quantum programming certification course provides the opportunity for an enterprise organization and the people within it to create a roadmap for developing your organization's competency in quantum computing, and then to be able to incrementally build skills through development of prototypes or proof of concepts that are more relevant to your area of domain. And finally, the objective is to get ready with the technology being developed and not necessarily wait for the technology to develop before adopting it. And I'll be happy to either engage in a discussion now or later on to follow up, where ICHEC and the Euro HPC Competence Center in Ireland, which ICHEC runs, basically offer services to support in learning about quantum computing and getting skills development within the organization. So with that, thank you very much, and I'll be happy to take any questions if there are.
So many thanks, Ventatesh. The Q&A function is available for those of you who wish to add any questions or pose or look for further information from Ventatesh. Last year, Ventatesh, you kind of brought us through what seemed to be the elements of the quantum computing ecosystem coming together. And in the 12 months since, there's been a radical change in terms of the parts of the ecosystem that have come together, supports that have come together. It's very, very tangible now. Could you just maybe give us an example of, and I know in your presentation you spoke about the degree of specificity for particular problem types, but for an SME who's maybe involved in the materials science space, could you just give me an example of how an SME who would seek to gain the advantages of quantum computing but has no prior knowledge of it, how would they engage? Like, is there a single place they go? How would they engage with that community, and how would they start to get involved?
What we have typically seen is in many of the sectors in enterprises, the learning pathway initially is to potentially learn through examples that are not necessarily to one's area. For example, in financial services, we have had discussions with our partners where they are open to learning about how optimization problems are for the logistics sector contribute to the development of algorithms. So what I mean to say is, for a material science organization, for example, it is not necessary that they have to start with how can quantum computing help me to define new materials or smart materials for their products. The first step would be to potentially understand how fundamentally quantum computing is different and quantum algorithms are different. So there are a number of well understood or well created use cases and examples. So a good starting step would be to pick up a few of those use cases through either existing learning material or reaching out to some of the national centers who organize, who offer training programs in them. So once we learn maybe some typical examples, then there is an opportunity to identify this is a small problem, small enough of a problem in material science, for example, for me to understand how the problem can be mapped onto quantum computers and where quantum computer can deliver an advantage.
So, and on that, I think there's a degree of maybe hand-holding, explanation, clarification, just a way of illustrating to the community where value will derive from engaging with the quantum computing community. And it would seem that the certification course is, a large part of getting that message across. Can you give us some sense of is that course available now? On what basis will it run? Are there costs associated with it? And who do you go to talk about it?
Certainly, yeah. So in terms of the cost, it is not finalized yet, but then the cost model is something that is based on the technology Ireland ICT SkillNet training program. So the training program is currently under preparation, and at least the versions for the executives and the managers is due to be launched in June, July this year. The course itself is meant to be delivered in a blended way. So there will be offline learning material, which is pre-recorded, but then there are also online live sessions where there is an interaction between the tutor, so to say, and the attendees of the training programs. The manager's version is typically meant to be for around 5-week duration, each week around half a day's worth of time investment. For the executives, it is typically a half a day to 1 day that is customizable. And as I mentioned, with respect to the cost model, typically ICT SkillNet training programs are subsidized for the enterprises within Ireland. So that would be kind of an indicative cost model. The prices for them are not fixed yet, but they would be announced relatively soon.
And again, I suppose broadening out the ecosystem point, the major players, the Googles, the Microsofts, are they doing their own thing? Are they coordinating? Are they contributing in terms of a community approach, or is it kind of a more siloed individual, the Google approach, the Microsoft approach? How are they driving this?
My answer would have been definitely different last year compared to this year, because there is a lot of synergy arising between the commercial developers of quantum technologies as well as the so to say the research community that is publicly funded. So a simple example is, for example, the software technologies or the software programming tools that are developed by the likes of IBM or Microsoft are increasingly becoming interoperable. So they are providing interfaces and support at a software level to be able to run the programs that are developed in one software stack within another software stack or other hardware devices. So there is an increasing synergy in interoperability of technology in the full stack approach that is being pursued by the hardware vendors or developers. In terms of skills development and learning, they still are quite fragmented because there is no so to say a one learning material or a best practice approach yet. So many of the courses address quantum computing from a more mathematical and quantum mechanics perspective, because they are naturally driven by the quantum physics and mathematics community, whereas in other places they are delivered from an end user approach where it's still considered a gray box or a black box in teaching material. So the community is still building a lot of training material. So don't get scared, so to say, if you find too much material. It's always a good place to start with any of the training material and identify whether you would want to dive deeper into the mathematics or maybe understand better why quantum computing is supposed to work better for certain problem types. So it's important for anyone that starts the learning curve in deciding for the first step whether you would want to understand from a functional approach or from a mathematical and physical approach, and then it's easier probably to navigate the learning material space.
And are those large players, are they cooperating by accident, or is there a coordinating body, or is it coming together purposefully or accidentally?
At a global level, I do not think there is any kind of standards organization or others driving the technology, etc. At a European level, for example, under the European Commission guidance, a quantum industry consortium has been established. It's called QUIC, QUIC. And basically, what it is a composition of technology developers and technology end users, not just within Europe from a global level, but then they focus on the development and adoption of technologies, quantum computing technologies within the European space, so to say. So it's not a standards organization yet, but there is a lot of discussion on how to bring coherence within the enterprise community in developing and adopting the quantum technologies. But it's still a very wide community where both the technology and the skills are pursued by the individual organizations.
Okay, and in terms of an SME who's bringing it back to an SME who's looking out to the future and trying to determine, given the last point of your presentation, which is kind of an encouragement to get on board sooner rather than later. An SME is looking forward, they're resource constrained, they know that maybe here is somewhere that's a particular advantage for me, but there's a path I have to go through. Maybe part of it is educational, but beyond that, it starts to become the cost of doing business in the quantum computing world.
Right.
Do you have any examples of kind of where those costs would start to arise? And I'll just sort of maybe preface this in that you had a very good slide with regard to the triumvirate of domain expertise, algorithm development, and then hardware. And to me, the three of those coming together represents a way of solving a problem, but potentially three particular ways of costing money. So what sort of financial model or what financial illustration, even though it's at these early stages, can you give us in how an SME would navigate that space?
Again, as you mentioned, that's a very good point, because for smaller sized or medium sized organizations, the investment or the ask of what does it take financially to kind of get into quantum computing is critical. What we have observed through our engagements is that a two-step approach is preferable, and that is not something that iCheck or we have identified. It is basically through the engagement with the enterprises in designing the quantum programming certification course that fell out of all of the discussions. The manager's version is something that is quite lean and quite short period of time, and hence the time investment required to understand where is quantum computing positioned, where can it be beneficial for the kind of work or the system or the domain that an organization works, to identify that level of understanding, and where can we get access to quantum computing infrastructure to have that level of understanding. That seems to be the preferred approach for many of the enterprises, where they invest a relatively shorter period of time, which is roughly around, so to say, 5 days, 10 days, and better understand the landscape of technology before investing longer people's time in learning the algorithms and developing a prototype and learning software toolkits. So that would be the second stage, where it takes a lot more time and financial investment from personal efforts to develop the skills within an organization. So two-phased approach is definitely something that seems to have emerged from the consultation. Now, in terms of access to resources, the learning material, access to quantum software simulators, and access to even certain quantum mechanical hardware devices, they are relatively available for free in many cases. So I think the access to resources in terms of infrastructure or training programs, there are a number of, so to say, inexpensive channels that are available at national, European, and global levels.
Okay, and again, because it's an emerging field with I suppose many different voices and a vibrant community, but will there be any one sort of singular contact point? Is it the national contact point? Is the place you go to start your journey, just to figure out, is this the right fit for me? Is this the right, even though you exhort people to look early, is it really for me? Is it, is my problem space adaptable to this particular technology? Is there one place they can go?
At a national level, given iCheck has the mandate to bring high performance computing to the national audience in research in enterprises in public sector, iCheck are one of the touch points where people or organizations can reach out to us. Even though we are not experts in the entire value chain of quantum computing, our purpose is to deliver the quantum computing platform skills development expertise to the audience. So we have a network, so to say, of technology developers and end users and training program operators at national European level. So we can deliver a certain set of skills, but then we would have definitely the channels to link to the rest of the ecosystem at national and European levels as well.
All right, so it's kind of go there, arrive at iCheck, and you can get to anywhere else.
So yes.
All right. Listen, I'd just like to thank Ventatesh for your time again this year, and yet another very illustrative view into how quantum computing has evolved, and the rate and the pace it's going is truly remarkable. And maybe next year, we'll have quantum computers on our desktops, or at least simulators on our desktops. But once again, I'd just like to thank Ventatesh for his time and remind the audience that the festival is running all week. We have a hybrid event on Wednesday, and to thank you all for your participation and your questions. I just realized, sorry, there's another question just popped in here at the end. I just want to maybe pick up this one last question. Will the certificates and the training you mentioned be available to individuals who want to break into the space, or just enterprises? Individual versus enterprises for the certification course?
There are different channels through which we are delivering the training materials. So for enterprises, for Irish enterprises, it will be predominantly through the Technology Ireland ICT SkillNet channel, but there are other programs which we can leverage to subsidize, so to say, the training programs delivery as well.
Okay, so it's kind of a watch this space, and you will be promoting it primarily through the SkillNet structures. Is that correct?
That's correct. And to answer Michael's question, there are other programs that you can leverage to address it from a price point.
Okay. Listen, Ventatesh, once again, just thank you, and thank you all for your questions and your interest. A fascinating topic. So we look forward to maybe talking or observing or seeing how it evolves over the time period. Thanks once again. Thank you very much indeed.
Thank you very much, Ian. Thanks, everyone.